And welcome back, everybody. So in this second video for this module on the diffusion equation on transport mechanism in porous media, I will talk about the diffusion equation this time. So last time we reviewed how, basic definitions of diffusion, where it's efficient to transport, mass through concentration gradients. And today we're delving a little more into what exactly do we mean by diffusion. And here's a quick video from the La Casa de Papel, or that was the original Spanish name, I suppose. Money Heist, they call it in English. Right? And you can see the Zeppelin here dropping some banknotes in the downtown Madrid, actually. And you can see how they kind of, from a point source in that Zeppelin, spread out before they reach the ground. So this is really a good example of, something that just diffuses away from, that point source and then reaches the ground, over tens of meters, if not hundreds, right? On the right-hand side here is another banknote from the Swiss bank. And so I assume it would be 10 Swiss francs. And the person here, represented is Euler. And I thought it was interesting because what we'll use today is a Eulerian approach, or a derivation of the diffusion equation, right? And Euler is one of the few scientists, right, that has a banknote with his face on it. So I thought that was interesting. Okay, so let's take this image of a bank vault, right? Continuing with this analogy of banknotes and where money spreads. So let's say we have finite volume and there's some money coming in, hopefully, some salary that we earn, and then money coming out, some expenses, and then, the vault would be your bank account, maybe. And so what stays in there, how much money do we have in a bank account? So it's just a mass balance, basically, or book balance if we talk about money. Okay, so the change, again, the change over time, right? Meaning how much money you have in your bank account, is the change at the boundaries, meaning the flux J, right? So J is going to be a flux for this lecture. The change of flux, over the change in distance here, or x, right? So again, this is in minus out, right? So dj dx is actually, so by convention, usually when we write dj, right, we mean J out minus in. So the accumulation, right? So the accumulation of money in the bank account, right, is minus dj, right? It's like how much comes in minus how much goes out. This is how much accumulates, right? So if dc dt, again, C is for concentration, but imagine it's just money in your account. The money you accumulate in a savings account is the money you put in minus the money you put out, right? So the money you put in minus out. So it's minus dj, okay? So this is why the sign. But other than that, this is literally the definition of, accumulation of mass inside that volume is, minus the flux at the boundaries. Now, what is that flux, right? So I've been talking about flux. What exactly is that flux when we talk about diffusion? And again, this is the characters of Money Heist, or we can think of a minion. And the game is, how do we get more, right? This is really what bank robbers, I guess, would want, to have, more money out. So how do we get more, more flux at that boundary if they come from here, right? So let's imagine we have a bunch. Again, you can think of these little dots as banknotes. You can think of them as, molecule moving around, anything really, particles, something, right, that we'd like to traverse and get to us. So how can we get more? Well, there's essentially four parameters, if you will, or four things that can, move things faster across, right? So one is a smaller distance, obviously, right? So if those two walls, right, are closer, obviously we're going to get more stuff out, right? So if it's the distance to traverse is smaller, it's easier, essentially. Same thing if we have smaller, again, molecules / smaller things, then, you know, they move more freely, so it's easier to, or they go faster, right? So remember from the last lecture, this is similar to the difference in diffusion coefficient in fluid or in liquids versus gas, right? So in liquids, because they're more dense, more packed, more viscous, if you will, it's harder to move through them. If you're in a gas, right, at, you know, higher temperature or just in a gas, molecules are very loose in there, so it's very easy to make your way through. So if you're a smaller molecule, it's just easier to navigate. Of course, if you have a bigger net, right, so bigger walls, let's say you were, you know, fishing and you have a net, right, the bigger the net you cast, the more stuff you get in, right? So again, the surface area of, you know, of the diffusing, of the diffusion, right, the larger the area, the more you get. And of course, the more molecules, so we're back to the concentration gradient now, but, you know, if you start with a larger number of stuff to begin with, then of course you'll get more at the end. So those four, you know, things are really what drives diffusion. Now, if we put this in an equation, right, so N here is the number of, again, particles, banknotes, you know, anything, molecules. So again, dN dt is how much, you know, you get, how much you accumulate. Now we can say this is a diffusion coefficient, so this is equivalent to the size of the particles, if you will. The concentration gradient, so again, this is how much particles you have to begin with. So the, you know, the higher the concentration gradient, the more molecules you have to begin with, and if there's none at the other end, then the more you get. The wall size, right, the net size, the area, and divided by the distance you have to cross, because of course, you know, the shorter it is, you know, the more efficient it is, so the longer it is, the less efficient it is, so it's inversely proportional to that distance. And there we have it, right? This is basically our diffusion equation. So if we write this as a flux, which is, you know, dN over A dt, so dN over A dt, which is number of particles per area per time, right, which is really the definition of a flux. So per area per time, then we end up with J equals minus D dC over dx. Again, A now is here. Okay, so this is your diffusion equation. This is really what the diffusion is. Let me bring that down a little bit. And again, this is what we call Fick's first law, and we'll see now in a second what the second law is, but this is really the definition of that flux that we've been talking about. Now, if we combine the mass balance, again, the mass balance is this equation I described in the very first couple slides here, where the accumulation is, you know, minus the flux over the distance. And now that we have a definition of the flux, we can put those two equations together, right, and find this equation where dc dt equals d squared c dx squared. And again, this is because if we replace here j by minus d dc dx, you can see that this is going to give us dx squared, and then we have d twice, so that's our d squared here, so d squared c over dx squared. And then the diffusion coefficient, if it's a constant, and we'll talk about this a little more, but being a constant can come out of the differential. So now we have it. This is Fick's second law after we put together the mass balance and a definition of the flux. Okay, so just to wrap up, we started with this question: how do we get more, you know, ping pong balls or more things across a volume? Found all four of the relevant parameters, put them together into an equation for a definition of the flux and a mass balance. Put those together and find the diffusion equation, which again is also known as Fick's second law. Okay, this is it for this lecture. In the next lecture, we will talk about advection and how the advective flux also can influence transport in porous media. Thank you.